Hello all. Now let us start. Yesterday we have seen zero ring. Zero ring itself means, I hope I am properly audible. Am I?
Yes, ma'am.
Okay. So zero ring is a set containing singleton 0 along with addition and multiplication. So this is a special kind of ring as you are watching, where 0 itself is the additive identity element and 0 is the multiplicative identity element also. Now let us move ahead. We have up till now seen that a ring is a structure along with addition and multiplication. So R along with addition must be abelian group. And as far as multiplication is concerned, multiplication must be binary and associative. And one more condition was there, multiplication must be distributive over addition from left as well as from right. Now let us see one by one what happens if multiplication is commutative. So if the multiplication is commutative, we call that ring as commutative ring. If multiplication is commutative, we call it as a commutative ring. And if suppose there is multiplicative identity element also present, we call the ring as a ring with unity. Unity means 1, which is the multiplicative identity element. So I would like to go one by one. I would like to revisit the concept of isomorphic. I want to show that ZRS is isomorphic to ZR cross ZS. This is the direct product. Only if the GCD of R and S is 1, means R and S do not have any common factor. In that case, ZR cross ZS is isomorphic to ZRS. So, as an example, I have written here Z14 is isomorphic to Z2 cross Z7. As we are watching, 2 and 7 do not have anything in common, no common factor other than 1. So GCD of 2 and 7 is 1. So we want to show that Z14 is isomorphic to Z2 cross Z7. So let us just move back to what is the concept of Z2. So what is Z2? Z2 means the set of all integers which leave remainder after division by 2. So if the number is divisible by 2, we call it as 0. And if the integer is an odd integer, we know remainder will be 1. So Z2 is 0, 1. As far as Z7 is concerned, what is it? Starting from 0, we have 1, 2, up to
6.
6. So these are the possible reminders as we know. Z2 and Z7 we have written. Now let us see what happens to Z2 cross Z7. If we have Z2 cross Z7, this will be ordered pairs. First element will be from Z2 to 0, 0, then we'll have 0, 1. In this way, the last element will be 0, 6. Now, taking 1 in the first position, we will have 1, 0. Then we'll have 1, 1, and so on. So the last element with 1 in the first place will be 1, 6. So how many elements do you observe here? How many elements are there? 7 to the 14 elements are there. In all there are 14 elements. So I would like to write here cardinality of Z2 cross Z7 is 14. Hope all of you agree. Now, one more thing I must tell you that this is an abelian group. As far as plus is concerned, this is an abelian group. Z2 with plus is an abelian group. Z7 with plus is an abelian group. So what is going to happen next? 1 will be the generator of this. You know, every element in Z2 I can write as 1. Element 1 itself is 1. 0 I can write as 1 plus 1. 1 plus 1 is 0 in Z2. So
Yes.
you can say this group is generated by 1. Talking of Z7, 1 can be written as 1, 2 can be written as 1 plus 1, 3 can be written as 1 plus 1 plus 1,
Plus one.
thrice 1, and so on. So instead of writing in the fashion of plus, can I write it as twice of 1? Can I write it as thrice of 1? I hope all of you agree. How I'll write 4? I'll write 4 times 1. Means I'm adding 1 plus 1 plus 1 4 times. So all the elements I can enlist this way. I hope all of you are getting my point. And when I reach to 7, 7 times 1. So it is 0. Do you agree? What I mean to say is instead of 0, I can write it as 7 times 1. For 1, I'm writing 1 times 1. For a 2, I will write 2 times 1. 3, I will write 3 times 1. And 6, I will write as 6 times 1. So every number in Z7, I'm able to write as some integer times 1. Do you agree?
Yes, madam.
Okay. So now proceeding the same way, in case of Z14 even, we can write the same way. So I would like to now move to Z14. In all, how many elements are there in Z14?
30. 0 to 30.
Is 0 to 13 means how many?
14. 14.
How many are there?
14. 14.
Elements are there. So Z14 starts with 0, 1, 2, up to 14. So as far as the cardinality of this set is concerned, it contains 14 elements, and Z2 cross Z7 also contains 14 elements. I feel you are getting. Cardinality is the same. Now you see how we'll be able to define element in Z14. So Z14 can be written as what? Any number. Suppose I want to write as n. How I'll write n? I'll write n as n times 1. Can I? One mistake I have done while writing the set. What is it? While writing Z14, I have done a mistake. What is it?
13 पर्यंत
It should be up to 13. It should not be 13. Z30, 14 means it ends with 13. Okay. And if at all I write 14 times 1, it means it is 0. Did you get me?
Yes.
Yes, 0 I can write as 14 times 1. So this way I can write my numbers. And now can you suggest me what should be our function? How will you define function? from Z14 to Z2 cross Z7. I want the function to be homomorphism 1, 1 as well as onto. So I would like to give you a clue. My clue is the way we express the number. How do we write n? N we write as n times 1. Any number I can write as n times 1. This is a clue to you. So how would you define this phi? Yes, anyone? How would you define phi? No? Alright. I have chosen n and n can be written as n into 1. I hope all of you agree. And now let me apply my phi on this n. By n what I mean it is n times 1. Hope all of you agree. Output will be n times ordered pair 1 comma 1. Ordered pair 1 comma 1. Did you get me? It is Z2 cross Z7. So it is the set of all ordered pairs. So I can write it as n times ordered pair 1 comma 1. So if not, I would like to help you using Venn diagram, or I would like to go like this. Go like this. The things are in front of you. If I mean to say 2 in Z14, how do I write 2? 2 I write as twice 1. Is it right?
madam.
Yes.
6 twice 1 and
Yes, it will be twice 1. Yes, it will be twice 1. So what will be the output? Twice 1 comma 1.
1.
Twice 1 comma 1. So image of 2 will be twice 1 comma 1. What is twice 1 comma 1? I'm extremely sorry. I rub this. First, let us decide what is the image. Yes. So I'm writing phi of 2. And what will be the output? Output will be twice 1 comma 1. But never forget that the first entry is from Z2 and the second entry is from Z7. So twice 1, what it will be in Z2? 0. Twice 1 means 2 and 2 divided by 2 remainder is 0. What will be the second position? Twice 1 is 2 divided by 7. I'll get it as 2. So what is the output? 0 comma 2. Okay. I want to check for what is phi of 5. Let me go for phi of 5. If I go for phi of 5, it will be 5 times 1 comma 1. Do you agree? This is going to be 5 times 1 comma 1. So what it gives me? 5 into 1 is 5. 5 divided by 2. Remainder is
1.
and 5 into 1 is 5. So the output
5.
will be 1 comma 5. Are you getting my point? Is the thing clear?
Yes, ma'am.
Okay, so this way you can show that this function is 1, 1 as well as 1, 2, and moreover it satisfies homomorphism property. How will it satisfy homomorphism property? Let us go for homomorphism property. See, you select two members from your Z14. So one member is n into 1, the other member is m into 1, and suppose I have their addition and I'm applying phi on this particular number. If I apply phi on this particular number, So what is going to be the output? So this is n into 1 plus m into 1 means actually it is n plus m. Do you agree? So this is going to be n plus m. This much times ordered per 1 1. Will it be so? Are you getting my point? This will be n plus m times ordered per 1 comma 1. Now this will be n plus m when divided by 2, whatever is the remainder. And this type here, this side will be n plus m. And I'll write base as 7. Do you agree? What I mean by this is remainder when divided by 7 and this is remainder when divided by 2. Is it sure? So very naturally, what this is going to be? This will be phi of n plus phi of m. So phi satisfies addition. Same way you can go for scalar multiplication of the numbers also. To be more clear, you can see over here. Always we can write this as 1 plus 1 plus and so on n times. So n summands. This is 1 plus 1 plus and so on m summands. So naturally the product is going to be nm summands. So n times 1 multiplied by m times 1, I can always write as nm times 1. So this is what you have. So this is certainly a kind of homomorphism as far as addition is concerned and multiplication is concerned. So it is a ring homomorphism, and being 1 1 and onto it is bijective ring homomorphism. So it becomes an isomorphism. So here you can watch the things. It becomes ring isomorphism. Is this fine? Now I would like to move ahead. So what we have shown here, Z14 is isomorphic to Z2 cross Z7. What I need to remember is, I just see what are the bases, R and S. If R and S do not have any factor common other than 1, we say ZR cross ZS is isomorphic to ZRS. This we have to keep in mind. Now I would like to move ahead with our next definition. As in the beginning I said, a ring in which multiplication is commutative, we call it as a commutative ring. If the ring has identity element for multiplication, we call it as a ring with unity. And the identity element itself we will always refer to as unity. So keep this in mind. Multiplicative identity element will always be called as unity. Now, I move ahead. There is a bit understanding needed. The word unit is different than unity. The word unit is used for multiplicative inverse, and unity is taken for multiplicative identity. So always keep this in mind. Multiplicative inverse is different than multiplicative identity. See here, let R be a ring with unity 1 not equal to 0. Because you know, if you take 0 ring, the unity is 0 there. So it is very necessary to mention what is your unity. So here we are saying R is a ring with unity 1 not equal to 0 and an element U in R is a unit of R if it has a multiplicative inverse in R. So if your element is having multiplicative inverse, then we call it as unit element. So I would like to concentrate on Z7. Just now we wrote our Z7. I would like to once again focus on it. 0, 1, 2, 3, 4, 5, and 6. Now what you observe? We are saying an element U is called a unit of R if it has a multiplicative inverse in R. So 1 into 1 is 1, it has inverse. If I go for a 2, 2 what's the 1 in 7? Z7. I hope you have tabulated it. So whenever I say I want answer to be 1, I would like to go for the table of 7, 7, 14, 21. If you want the answer to be 1, you want 7 plus 1, 14 plus 1, 21 plus 1 as your answer. Likewise. So 2 what's 1 more than multiple of 7. This we mean to say. So 3 2s are 6 is not there. 2 4s are 8. Yes. 2 4s are 8. So inverse of 2 is 4 and inverse of 4 is 2. So because 2 has inverse, I can say 2 is a unit element in Z7. 4 is also a unit element in Z7. Now let us move to next 3. I know 3 5s are 15. So 15 means 14 plus 1. So the inverse of 3 is 5 and inverse of 5 is 3. You can still go ahead and talk of 6. 6 is 36. When 36 divided by 7, it is 7 5s are 35 and remainder is 1. So 6 are in Z7 is what? 1. So 6 is its own inverse. 1 is its own inverse. Yes?
We can multiply by its own self also, no? It can.
Not getting your question.
Means 6 can multiply by its own self, no?
Yeah. This can happen. If you multiply the number by itself, will also do. Only the thing is you cannot go out of this set. The elements with you are 0 to 6 only. And 0 is never invertible actually. So we will not go for 0 because 0 into anything cannot be 1. Okay. So that's why we are saying every non-zero element. Okay. Yet we are to talk about this. Whenever we talk about unit element, we are dealing with a non-zero element. So 1 is invertible, 1 is its own inverse. 2 4s are 8. It gives us remainder 1 when divided by 7. So 2 is the inverse of 4 and 4 is the inverse of 2. Same happens with 3 and 5. 3 5s are 15. So 3 is the inverse of 5 and 5 is the inverse of 3. As far as 6 is concerned, I know 6 are 36. Remainder is 1. So 6 is its own inverse. Followed? So we try to define a unit element. When to say an element is unit, suppose I'm having element A. When can I say A is a unit element? If there is any other element B such that A into B happens to be unity, then we say that. So A into B should be 1. Naturally, the same time B into A also happens to be 1. So B is the inverse of A. And we write it as A raised to minus 1. So A raised to minus 1 is B. Means B is the inverse of A. I hope you followed it. So this was the definition of unit. Unit means multiplicative inverse. And if suppose every element is invertible except 0, then that particular R is known as division ring. That particular R we will call as division ring. Okay. And if that division ring is commutative, then it is known as a field. So field is nothing but a commutative division ring. So in FY, you have already learned that the set of real numbers is a field. You have learned field axioms for real numbers. So as far as the set of real numbers is concerned, it is a ring. Every non-zero real number is invertible. You know, if I say A is a real number, then 1 by A is also a real number provided A is non-zero. This you know. So R along with usual addition and usual multiplication is a field. Now we impose the condition of commutativity. If it happens to be commutative, if it is a ring with unity, if every non-zero element is invertible, then we call it as field. But if it is non-commutative, only one thing is violated, non-commutative, but it is a division ring, then we'll call it as strictly skew field. So at this moment, I won't insist upon using this wording. Only keep in mind that field has to be a commutative division ring. Is it okay? All right. Now, I just move a bit ahead and I'm just defining what is meant by subring and what is meant by subfield. It's but sure whenever we say sub, so the same kind of structure is there. So if at all you are having R as a ring, and suppose R dash is subset of R, and R dash satisfies all the conditions that are required for R dash to be a ring, but because it is contained in R, we call it as a subring. So subring itself is a ring, but it is subset of some bigger ring. So we call it as subring. Same thing happens for subfield also. We know subfield is a subset of a bigger field and satisfies all the axioms that are required for a field. Is this fine? Okay, only one response I got. Okay.
एकदा सांगा ना परत.
परत एकदा सांगायचं म्हणजे तर आपल्याला माहिती आहे whenever we say we talk about any operation, we talk about its binariness. Just a minute, let me move to this side. All right. What are the things required for any operation? Binariness. Unless it is binary, we don't proceed. Next, we want associativity. Next, we want identity element. Next, we want inverse with respect to that operation. Next, we want commutativity. I feel all of you know this very well. Now see, you are having R as a set, addition, you know, R plus forms an abelian group. So all these 5 conditions hold over there. And as far as multiplication is concerned, We don't insist upon all those. We insist only on binariness and associativity. And one more condition is distributivity. We insist on multiplication should be distributive from left as well as right. Why we are saying left and why right? Because we don't insist upon commutative. So R plus dot happens to be a ring. If R plus satisfies all these 5 and this multiplication satisfies only these 3, we call it as a ring. Now if at all there is identity element present, we call it as a ring with unity. Followed me? If identity element is present, we call it as ring with unity. Again, if the ring is commutative, we separately call it as commutative ring. And lastly, if suppose identity is there, ring is commutative, and every non-zero element has inverse, then we call it as a field. Followed now? Got the meaning of field? See, if my set is an abelian group, basically it is a ring. So I need not go much. Abelian group. What is abelian group?
5 condition commutative.
Yes. So R plus satisfies 5 conditions. Binariness, associativity, existence of identity, existence of inverse, and commutativity with respect to addition. We call it as abelian group. Now, along with that, you have multiplication, and multiplication satisfies 3 conditions: binariness. So I need not write it, I think so. Let me mark it with blue. Binariness, associativity, and distributivity over addition. I call it as simply ring. Now it is a ring. And suppose in addition it is commutative. Multiplication is commutative. What we call it as? Commutative ring. If multiplication is commutative, the ring is called as commutative ring. If there is identity element for multiplication with respect to multiplication, we call it as ring with unity. We call it as ring with unity. Now, along with existence of unity and commutativity, if every element has inverse, only 0 is not having inverse, rest all have inverse, we call it as a field. Followed me?
मॅडम मला
हा.
बायनरीने सांगा ना परत एकदा.
बायनरी म्हणजे आन्सर तुमच्याकडे आहे. 2 एलिमेंट मल्टिप्लाय केलं की त्याचा आन्सर पुन्हा त्याच सेट मध्ये असेल तर त्याला आपण म्हणतो बायनरी.
आणि आर प्लस मध्ये ऍडिशन केल्यावर
ऍडिशन केलं त्याचं येणारं उत्तर आर प्लस मध्ये, आणि मल्टिप्लिकेशन केलं तर आर प्लस डॉट असं पूर्ण विचार करतो आपण.
आयडेंटिटी 0 येईल याची आणि इनवर्स.
Identity for addition is 0. Identity for multiplication in real numbers is 1. Inverse in real numbers is 1 upon reciprocal आहे. Is it okay?
ऍडिशन साठी पण
I will help you with an example in our next lecture. Okay.
ओके मॅम.
Okay. So till that we will stop here.